All right, good afternoon, everyone. TGIF. It's Friday, 12 o'clock noon. Let's get started. How you folks are doing? Happy it's Friday. Doing okay? Yeah, I'm good. Thank you. I'm glad it's Friday too. It's been a rough week, um, for me. Stressed out. I can definitely feel that. So believe me, I think I know what you feel, especially with test three. Yeah, let me answer the question about our schedule for next week because it's a holiday. Let me check the. Yeah, let me start sharing something. I'm just reorganizing Windows. Bear with me so that I can have all the panels that I need on the screen. Yeah, so poll one is available for anyone wanting to nominate about their least favorite problem on that test. Like I said, we do hear your concerns. We do listen to what you folks say. So, let's collect their information first to make sure that all people in the class have an opportunity to express their opinion, and then we can decide what we can do about it. How does it sound? The TA told you no fork and exec would be on the test. Well, I would like to know which TA that was, because it was, if that happens, then you should still look at their course notes and their submittee forum. If you find that your TA provided you with a contradictory information, you need to double check, okay? Because it was clearly on the submittee forum under the topic about the exam scope, and I mentioned it in the lecture, definitely, and it was also in the text file in the notes for the corresponding lecture when we were discussing that. Okay, so you use 6PTSD. Oh, I feel so bad. Sorry, folks. It wasn't meant to be that way. But yeah, someone says it was totally doable with more time. So that might, that might lead us into the discussion of, why, so many people ran out of time. What went wrong with other problems, so that people didn't have enough time to finish question 6, because yeah, and fork and exec took a lot of time. It shouldn't have. That's the thing. So if you spent more than 20 minutes on the fork and exec problem, that's probably a little bit too much. And writing MIPS by hand takes a lot of time. It does, but the thing is, maybe if you find yourself writing too much, it's a sign that you are doing something not in the most efficient manner. Once we release solutions to test 3, you will see that really their first problem is like less than 40 lines of C code, and all MIPS problems are like 20 lines maybe each, maybe 25. So if you found writing like 80 instructions, that's probably you're not doing something exactly right. Yeah, handwritten MIPS is nightmare. I know, I mentioned before, I wish I could let people use their laptops with no internet. Fortunately, with the kind of circumstances we are in, it's not feasible. We have to have pen and paper exams. That's the requirement of their department. and the School of Science, and we do not have a testing center where students would be allowed to take their exams on computers that have certain software installed, just not internet capability. Uh, yeah, so someone is saying that data structures tell people how many lines of code the problem would take. I tried doing this in the past, and I found that it was actually doing more harm than good to many students. Because imagine I wrote my solution in 20 lines, and some student would write their solution in, I don't know, 25 lines, and there's nothing wrong with the solution. It's perfectly correct. Yes, maybe it's not as efficient or as concise, but there's nothing wrong. And I don't want that student to think, oh, I'm doing something wrong because I'm over 20 lines. Okay, so that is the main reason I don't like to give any kind of target number of lines, just to not to intimidate students who might just use a different style of programming that is a little bit more verbose. Okay, yeah, let me answer the question that appeared somewhere in the very beginning about our schedule. So I don't think this holiday affects us at all. So if we look at our course schedule, then we are here 10/8, and as you can see, we are a little behind our original plan. So we were supposed to start Boolean logic today, but we are still finishing chapter 2. But 10/12 is our regular Tuesday, so the holiday does not affect us. We have our lecture as usual on Tuesday. Okay, and yeah, I know many of you are sharing what you feel about question 6. So I will save the chat and I will read it to make sure that that I'm not missing anything. Speaking about saving chat, please, the panelists, do not end the meeting for all. Okay, because to make you a panelist, to give you the powers to answer Q&A, we have to make you co-host. And then if you end the meeting, if you leave the meeting and Webex asks you, do you want to just leave the meeting or end the meeting for all? If you end the meeting for all, it ends the meeting for all, exactly as it says. So it just, kicks everyone out. And in Webex, if you didn't save chat while the meeting was in progress, there's no way you can save it afterwards. That's the way this software works. Sorry, and that's kind of a little annoying to me. But there's nothing I can do. It's just the way Webex works. And I like to save chat so that I can then read it afterwards and see maybe I missed something, or just read all the opinions that you folks are sharing in the chat. So please, for panelists, do not end the meeting for all at the end of the meeting. Okay. And speaking of the panelists, do we have? Oops, I didn't. Let me stop sharing for a minute. And yeah, could our panelists for today please say something in the chat so that I know they're here and that we are good to go? Ketu? All right, I see 2 of the panelists so far. Other panelists are you here, folks? Yifong, Josh, Devanshu. Oh, Devanshu's here. Okay, cool. Yifong. All right, and I think we just missing Josh. Okay. All right, so it doesn't look like Josh is here, but we have 4 out of 5 panelists, so I think we're good to go without nominating or without bringing additional panelists in. And so let me start sharing again. All right. So a few things I wanted to talk about. Yeah, in their continuation of the topic with test three. So like I said, we are aware, and please keep sharing how you feel on in the chat, and feel free to do the same in submittee in submittee forum if you would like, and we will try to be fair and do something about it. So also, if you have any ideas of what would be the best, the fairest, I would say, way of helping you folks with test three. I know it's retroactive, so we cannot go back in time and change anything. But if you think there's a fair solution that would make you feel better and not so stressed out, I'm definitely willing to consider that. And we just try to be fair and realistic, right? We cannot give everyone A on this exam. Delete question 6 would I'm sure would be felt very unfair to students who did get question 6. And I can tell you up front, I looked at some of the submissions, and I saw at least one submission that I think is going to be, well, if not pure 100, it's going to be very close to 100, right? Because all 6 questions were answered, and the first glance, the answers looked correct to me. Okay, so some people did get, pretty much everything or close to that. So it would be unfair, I think, to just deprive them of their work and not give them any credit for the work that they've done. Okay, so that's why I think we should be looking for something that is perceived as fair by by most students. And yeah, canceling an exam is not an option, given everyone is not an option. Well, extra credit is something that I was also thinking. Okay, so just make that one problem extra credit, and yeah, that I think we could do. Okay, so please share what how you feel about it, what you think can be done or should be done. Just try to be reasonable and fair, and we can come back to to make this decision. So I will accumulate all feedback. We can come back to this decision closer to when grades are ready for our test. So our TAs and mentors are working on grading the test, so they have uploaded everything on Submiti, uh, and uh, and we'll start the actual grading hopefully over the weekend. Okay, if Q6 would be extra credit, would there be no curve then? Well, Q6 is 20 points, so if we make their exam 100 points, what used to be 80 points for the other 5 problems, then I think that's actually more generous than a curve, right? But like I said, just put everything that you think would be, would it be a good way to handle that? And I just don't want any of you, to be stressed out and feel bad, feel under a lot of pressure. So that's what I'm offering. I can do on my side. Someone says, I printed out example of fork and exit for the exam. That was really helpful. Yes, remember, we allow you to bring any printed materials on the exam, right? Anything you want at all, like textbook, all their practice problem solutions, anything. And I'm glad people are finding that helpful, because that's the way it was supposed to be. Okay. ETA when homework 2 grades will be released. Yes, some of you noticed they were accidentally released. So Submiti has a glitch with dates, which confuses us quite often, because we think we said that we moved the dates, but they didn't actually move, and that caused homework 2 grades to be accidentally. It made an impression they were released, but they were actually not. Those grades are not ready, and their latest, as of this morning, that I heard from our TAs, is that we should expect homework 2 grades be done on Saturday. So that's the thing. Okay, that's the plan. Okay, and homework 3 is out there, so please start working it. We will talk about some of the things that you will need for homework 3. Yeah, most people didn't realize fork and exit were on the exam, but did you look at practice problems? Practice problem with the fork was exactly there, and it was actually more complicated than the one on their exam, and someone was asking me about it. Well, yeah, the weight of different questions, of course, if we only have 6 questions, right, we cannot make each question 10 points, right? So we have to, make questions, you know, close to 20 points for longer coding questions and, 10, 15 points for smaller questions. I think that's reasonable. What do you think? Okay, so one point I wanted to bring across is that MIPS is a programming language, of course, as you as you already know, I'm sure. And as with any programming language, you have to practice it. You have to write programs to learn that language. You cannot, most people would not be able to learn a language if they do not practice it. So ask yourself, how many programs, MIPS programs, did you write yourself before their exam? Okay, and if that answer is, 2 from the lab, or 3 or 4, that's not sufficient. So you need to practice the language if you want to do well in it. Even if you just looked at our solutions that we posted, that's not their equivalent experience, right? It is a lot easier to look at their existing code and like go over it, and yeah, it makes sense. I see what's going on. I can do it. But then it's a lot harder to actually synthesize, write your own code. Labs in Zybooks is a great practice. So, and that is something that I wanted to show you actually. So this is their breakdown of the activities and labs from Zybooks for week number 5, which was exactly the material that was on the test. And so and it is sorted in by the total number of activities that students did, and just look at those numbers. So we have 6 people who did more or less half of their labs and questions or more, and so those are percentages. So 82.27 is 82%, right? So pretty much everything. So, my deepest respect to these 4 people who are actually doing their due diligence. And, a few people somewhere are around the middle, but, like a lot of people with just straight zeros. So that's my point. In the textbook, there are lots of problems at the end of the chapter in those exercises. And in Zybooks, there are even more opportunities to practice because there are Zylabs, right, which do not exist in our textbook, in a print textbook. So this is added value from Zybooks, but excuse me, they are they are your chance to practice, right? And unfortunately, very few people, even among those people who did subscribe to Zybooks, very few, actually use Zybooks to their full potential, I think. Okay, so if you are subscribed to Zybooks, please use it more. It's a great tool, I think. And if you are not subscribed to Zybooks, it's you can still do your problems. So I'm showing here in at the end of the chapter, so that there are problems, and if you look for exercises, okay, so here are all the things that appeared on the exam. Translate C to MIPS, starting from very simple things that actually appeared in the slides to things that are a lot more complicated. All right, so definitely over 10 lines, and there's a bunch of those problems here, right? Most of them relate to MIPS. conversions from hex to binary, two's complement notation, and all that stuff. Okay, so and that's in the textbook. And one other thing that my TAs actually asked me to mention to all of you, to the entire class, if you're using a paper, so if you're using Zybooks, there's there's nothing else you need to know. If you're using a paper textbook, please make sure you're using the latest edition, 6th edition. So we had some people on the previous homework submitting problems from the wrong edition of the textbook, and I mentioned in the first lecture that we are using the latest 6th edition of the textbook, and that's the edition that you need to get. And there was even a picture of the front cover of the textbook that we are using. And 6th edition cover is very different from the 5th edition. So 5th edition was kind of white, more or less. 6th edition is kind of bluish, so you cannot really mix them up. So please make sure you are using the right edition of the textbook, so that you can get your textbook problems right for homework assignments that involve textbook problems. Okay. Someone says we should have focused on homework 3 and get more practice for MIPS before we take exam on MIPS. So that practice was basically the lab. Okay, and we, if you notice, there was nothing except some basic MIPS instructions and conditionals and loops, which is basically conditionals. Okay, so homework 3 is a lot more involved. Homework 3, you will need to do dynamic memory allocation. Homework 3, you will have nested loops. So none of that was in their exam. Okay, and we have to, topics on the exam, we have to cover. We have to have questions that were covered by the material. Okay, is that making sense? I know it may not be the answers some of you are hoping for, but unfortunately, we have exams every 2 weeks. That's the way this class is, and we have to, test those small topics, during the course of the semester. So it's not like, and the added advantage is there's no final exam. So hopefully you understand where I'm coming from, and the importance. Like if we don't have something tested on the test, on the exam, practice shows most people would not even look into that material. So if I say, for example, formula for integrated circuit yield computation is not going to be on the exam. There will be very few students who would actually read that material. Most of the students would just skip it. Oh, if it's not going to be on the exam, I'm just not even going to bother with it. Do you agree that that's exactly what is happening? Okay, so that's why, and my goal is not to torture you, of course, and to stress you out. My goal is to make sure that you understand the material that this course covers. And I know maybe some of you think it's not the easiest material. Definitely, I agree. Some of you may think it's not useful. I disagree here. I think this material is useful if you want to say that you are a computer scientist, or you are, a qualified software engineer, software developer. You need to know how things work a little bit under the hood. We don't go, very deep into the electrical engineering side of things, but looking under the hood of what happens when you write your C code and how it actually runs and how computers compute. I think that's an important skill that all computer science students need to be exposed to. All right, so that was my point. Please practice more. If you need me to serve you more practice problems writing MIPS code, just let me know. I will. There are tons of such problems floating around the internet, so you can of course find them yourself if you want me to find them for you, and can bring them up in a single document. A few of those problems I can do it. It's not an issue. I probably won't be able to write solutions to all of them, but if you give me your solution, I would certainly be able to verify if it looks good or not. Okay. So yeah, please, if you want me to do something, please put it in the submitted forum, right? Because I'm hoping to save the chat and read it afterwards. But Okay, yeah, and Zybooks offers a very convenient analytics tool to the instructor. So I just wanted to show you for week number 5, Zylabs, for example. Okay, so we have people, almost no one did any Zylabs. Okay, you can see, that statistics. Average completion is basically 0. Average time is 0.11 seconds. Okay, and that active someone looked for 10 seconds at one Zylab on the 29th, and nothing was happening before the exam. Okay, so like I said, I will try to do my part in to help you out, folks. But please do your own due diligence, and please do prepare. Maybe rethink how you prepare for exams, especially on topics that involve programming. And it would be pen and paper. Like I said, sorry, there's nothing you can do about it. Okay, so yeah, renting mode off. Let's actually talk about something more pleasant. So on one, homework 3. Okay, so let's actually review some of the topics that are not directly in the slides. They are in the textbook, and both in the paper textbook and Zybooks. So if you look under week number 6, and if you look at here, memory usage, no, not even here, but MIPS simulator. Yeah, we are now in week number 6. Okay, and then oops, .NET Simulator. Sorry, it is SPIM 629. And of course, in their textbook, their numbering would be like it's actually in Appendix A, I believe. So because for Zybooks, I rearrange stuff. So what we need to know for dynamic memory allocation is really one simple thing. This system call 9, which is called S break. Okay, so again, in the textbook, in the physical textbook, it's under Appendix A, and it's really that is one thing where you would probably agree with me that it's actually much easier than allocating memory in C using malloc or the friends. So you just make this one single call to syscall with v0 of 9, and you pass in the amount of memory you want to allocate, and the result is in v0 is the address. So it's basically like your malloc. Okay, and that's pretty much it. So how do you free the memory? Well, that's even easier. You call S break with the syscall 9 with the amount which is negative. So if you requested 20 bytes at some point from dynamic memory to deallocate that memory, you request negative 20 bytes, and that's all you have to do. Okay, so that's pretty straightforward. Hopefully, let's actually look at an example. So hopefully all of you are reviewing the examples that I'm posting under lecture notes. And so where is it? Just give me 1 second. Sorry about that. I lose that example. Okay, just give me a second. I will find it. Might have moved it to the wrong directory. Just bear with me, please. It's called alloc. It is under lecture 11. Okay, but okay, I should be back now sharing with you. Yeah, it's under lecture 11, but I just somehow didn't have them loaded. All right, so here's alloc. Alloc example. All right, and so let's see what's going on here. So basically, we want to allocate memory for the array. We put the length of the array, but we need to remember that we are allocating memory. We might have to multiply it by 4 if that is the array of integers, right? Because each integer is 4 bytes. So, 10 is the number of elements in the array, but we want to shift it left by 2 positions. So that is multiplied by 4 so that we have the proper number of bytes that we are requesting. And then v0 is 9, and we make this syscall. Okay, so that's that's it. And another example here is we are allocating memory. No, that's it. Yeah, so everything else we're just using this allocated memory. So the address of that allocated chunk of memory is returned through v0. So we want to make sure that we save it, right? Because that's our pointer. That's the address that we are going to use. And you can see that we are using that as just, a regular address so that we can, let's say, move values from that address, that is a load from our array into this register A0 to, print it, print integer, and so forth. Okay, so that's really very easy. And yeah, someone was saying that they're still trying to wrap their head around shifts. Yeah, shifts are very common. They're very efficient from the hardware standpoint. So please make sure that you that you know how to use shifts. And in many cases, they are a lot more convenient. I noticed some of you on the test, they were trying to use multiplication, the mul instruction. You could do that, but you would probably have to write more code than if you just used shifts strategically, and especially in problem 6. And someone was saying problem 6 was really unnecessary. It was it was the same but just more complicated, but it's not exactly true. So I wanted to kind of point out why the problem 6 was actually there. If you think about other MIPS problems, well, there were 3 things related to MIPS, right? So there was this problem with just give their values of registers after executing this this piece of code. So you didn't have to write any code yourself. The code was given to you. Then another MIPS problem was we gave you the C code and asked you to translate it into MIPS. So you had to write your MIPS code, but everything was given. So it was just literally do what this C code does just in MIPS. Okay, so it was kind of mechanical. It still required, of course, knowledge of MIPS, but it was more or less mechanical. You didn't have to think how to solve the problem. You just had to, kind of translate, from one language to another. And then problem 6, and the reason why it probably turned out more challenging to many students is you actually had to write your code to synthesize the code to solve the problem. And that's that's how you do this in real life, right? So you are rarely lucky enough that someone gives you code and just asks you to translate, right? So most common scenario is they give you the problem and just ask you to solve it. Do this, with your program. Write a program that does that, and that was exactly problem 6. And their overall solution, like when I share my solutions, you will see that it's like 20 or 25 give or take lines of code, but you had to use and it has only one loop, and it uses all the stuff that we learned. But yes, it does use masks and shifts heavily, and that's what makes solving this problem efficiently possible. Okay, making sense? All right. How would we create a matrix with this? How would we save pointers to the individual rows? So you save the pointers in registers, right? Registers can hold 32 bits, so you can store integers in registers, you can store addresses in integers. And to allocate memory, you just compute how much memory you need to allocate, and then you put that amount in bytes in A0, and you call syscall sbreak with which is syscall with v0 of 9. Okay, that's it. Uh, Hopefully you agree. It's easy. All right. So let's now move on. So hopefully we covered that, and and the other important thing that we need to talk about is procedure calling. So that is something you definitely need to do on your homework, and of course it will be sorry folks if I disappoint you, but inevitably there will be a MIPS problem on the next exam where you would have to write MIPS code with procedures. Okay, it's extremely important. We simply cannot let it go just like that. So it will be on the next exam. So procedure is a piece of code that you anticipate will be reused multiple times. So you want to structure it so that you can call it multiple times. And there are no function call instruction per se in MIPS. So you just have to do jump, but that would be a fancy jump because that jump would need to remember where to return when the callee is done. So the terminology that we need is caller and callee, right? Caller is the code that calls a procedure. Callee is the procedure that has been called or is being called. So the procedure calling thing is really straightforward. So if this procedure takes any parameters, we need to put those parameters in registers according to what their procedure expects. Then we transfer control to procedure. So we do that special jump. It's called a JAL, J with address linking. And then our procedure starts executing. We need to acquire storage for the procedure, like for any local variables that it might be using, or we might need to allocate space on the stack for whatever that procedure needs are. We perform procedures operations, the code of the procedure, and then we place the result in register for the caller. That is the return value. And then we return from the callee and back to the caller. Do we need procedure calling for homework 3? Yes, definitely. Okay, and so as soon as we bring up the procedure calling, we need to kind of agree on how we use registers and what their convention is. So arguments are passed through those registers, A0 through A3. And that's why they're called A registers, right? There are only 4 of them. So if you need more registers, if you need more arguments, you have to pass them through stack, right? Because there are only 4 argument registers. And return values are returned through registers V0, V1. And if you think about the example that we just went through with sbreak, remember how before we called syscall, and syscall is not a procedure, right? So it's a little different, but it follows the same convention as procedures do. So we put something in A0 before we called our sbreak syscall, And that was the argument, the number of bytes that we were requesting, and the return value, the result of the syscall, was returned to us in V0. That was the address of the memory that was allocated for us. So T0, T9 are temporaries, and they can be overwritten by their callee. So the caller is responsible for saving any of those registers that it is using before calling a callee. That is very important. And then S0, S7 are so-called saved registers. They must be saved by the callee. So for S7, S0, S7, the caller expects that the callee does not change those registers. And if it does, then it restores their values, the original values, before returning from the callee to the caller. So the caller doesn't have to save S0, S7 before calling a procedure, but it has to save T0, T9 that it might be using. Of course, we are talking only about saving stuff that is being used, right? If a particular register is not used at all, you don't have to worry about it, right? Because it's not going to change. From the caller standpoint, if you're using T0, T9, solve them before calling a callee, calling a procedure. Don't needs to save S0, S7. From the standpoint of the callee, it's the opposite. They can use T0, T9 and change them any way they like. They don't have to save them, but they do have to save to preserve the values in S0 and 7 and restore them before returning to their caller. Who saves S0, 7? Their callee must save S0 to S7 if it is using them, right? If the callee, if let's say your callee is using only T0 to T9, don't worry about S's. You don't change them, so you don't have to save them. You would save that all in the stack exactly, and we are getting to what that stack is and how to work with it. So GP is a global pointer for static data. We will look at it in a minute. Stack pointer and frame pointer allow you to work with stack. You would mostly deal with SP because that's the register that you will need to change as you are using your stack, as you are saving or we say pushing stuff into the stack, because stack is really a last in first out data structure. So hopefully you remember that. I hope you heard this abbreviation in data structures or in CS1. So LIFO, last in first out. So that's stack. So which means that if we push something to the stack and then we pop something off the stack, we pop the value that was added last. And there are no dedicated push pop instructions in MIPS, so you just have to treat stack memory as memory and just use load word, store word instructions to work to actually implement your push and pop. We still say push and pop for convenience because that's really what it is. So SP tracks the tip of the stack, and if you want to push something in the stack, then you have to update SP, and when you pop, of course, you'll update SP as well. And FP is the base of the frame for that particular procedure. So when the procedure is just invoked, SP and FP are the same, and then if there are nested procedure calls, then FP would always correspond to the base address of the frame of that particular procedure. And RA is the return address. This is the register that is used to store the address that contains their instruction that should be executed next in the caller. So when the caller called callee, the callee returns, and the processor needs to know which instruction to execute after that. That would be the instruction in the caller that immediately follows the instruction that invoked the callee, the JAL instruction. So this address needs to be saved. And we can look at some examples. And so this is a procedure called leave procedure. Sure, thank you. I can zoom in. Yeah, thank you for reminding me. All right, so here's our main. So first thing that we do in main, and now we can talk about this since we covered SP. Note how we decrease SP by 4 because we are preparing to push value into stack. So we moved our stack pointer 4 bytes low so that we have room to save 4 values, and those 4 values is the contents of register RA. Okay, so if we plan on calling any procedures, that call, when we do JAL, it will overwrite RA, and we want to preserve it so that when we return from our procedure, we return to the proper caller, right? So obviously, when they're nested procedure calls, then we have to remember all the return addresses through the entire call chain. And there's only one register, RA, so we can only have one return address stored in the register file. So all the other return addresses in the call chain need to be saved explicitly in the stack. And that's exactly what this instruction does here. So these two instructions is basically push RA onto the stack. And then before we return from this procedure, in this case it's main, we have to restore RA. So note how we first read the value, load the value from memory and put it into RA, and then we adjust our stack pointer SP by the value that is the inverse of what we used for push. So when we pop, we first load and then we adjust SP by +4. And of course, you can read multiple things. You don't have to. So if you need to save 3 values, 3 words in stack, you can adjust this. You don't have to do this in increments. So you can just do add I SPSP -12, and then you would do store word RA 0 SP, store word RA, or whatever other value you need to store 4 SP and 8 SP. Okay, so you can store multiple, you can push multiple things at once, and then correspondingly you would have here 12 when you pop from the stack, and you would have 3 LW instructions with the same SP base address but different offsets, 0, 4, and 8 if you had previously pushed, and now you're popping 3 values. All right, so that's, and to actually call the procedure, we do JAL, and that makes the processor to start executing code from that label, and also puts the return address of this instruction, the next instruction in the caller. It puts that address into the RA, so that when the procedure is done and calls JR $RA, it returns exactly to this instruction. That's the instruction whose address is saved into RA. And everything else in this leave procedure is pretty uninteresting. So it's just performing this computation, and nothing fancy is going on here. But the important thing is this procedure uses S0 here. How do you know if the procedure, if any instruction changes anything? So the destination register is always the first register. So this sub will write into S0. And that's how you know. So if any of your register bound instructions use S0 as the first argument, you know that it's gonna write into that register, and it's a saved register. So the callee, leaf is a callee, needs to save that register on the stack, and we do exactly that here. It's the same code that we've seen previously in main. And before our leave procedure returns, we need to restore the original S0 from that we saved in the stack. So as far as main is concerned, S0 has never changed. And it doesn't matter that main did not use S0. It is the responsibility of their callee to save all S registers and then restore their original values if they are changing them. And leaf is changing S0, so it has to push it into the stack and then restore it, so that their caller doesn't notice any changes in any of the S registers. And note how that doesn't apply to T's, because a procedure can change any T registers. It doesn't have to worry about saving them. But what if main did use T0 here? What if there was some code that performed some computation, put the result in T0 before calling leaf, and then leaf is called? Of course, it's going to spoil T0. And we just mentioned leaf is not obliged to save T0. So when leaf returns, here in the next instruction, T0 would be changed and main would see that change. And that means that it is the responsibility of the main to save T0 before calling leaf if main is using T0. Okay, is that making sense? All right, so and this procedure is called a leaf procedure because it is not calling any other procedures. So, if you build a procedure called tree, this procedure would be a leaf in that tree. It's not calling any procedures itself. And because of that, okay, so you see it's a little easier for the leaf because it doesn't have to worry with saving RA. If a procedure is calling other procedures, is called non-leaf. So our main here is non-leaf because it is calling a procedure, and because of that, it needs to store RA. That's the additional responsibility of a non-leaf procedure. So the caller takes care of temp regs while the callee takes care of saved regs. Yes, so for any procedure, if it changes saved regs, it has to restore them. If it changes temp regs, it doesn't have to. But if you are the procedure, a non-leaf procedure that obviously because it's non-leaf, it calls other procedures, right? That the caller cannot assume that temp regs would not get changed by the callee. So if it uses them, it has to save them. All right, so let's go back to what we were discussing. If we use a register but want to keep the old value, we save it on the stack. Exactly. Yeah. So stack is your memory. It's like big compared to only 32 registers that you have in the register file, and we know that there are conventions. So, like typically, for temporary values, you can only use these 10, right? And then 8 more S's that come with an additional headache that you have to save them. But at most, it's 18. If you need more data, to work with at the same time in your procedure, then you have to use memory. You can either have statically allocated memory from their data segment, which we'll talk in a minute, or you use your stack. And another important note is, so if your procedure is using certain registers, most often than not, it can use the same registers over and over again for different purposes. Okay, so a procedure can reuse the same registers, right? So for example, you computed some and put it in T0, and then you can, use that sum in some other computation, but you no longer need that partial sum anywhere else. So then you can reuse T0 for some other, for some other values. So it doesn't mean that you have to, store each single sub result forever in one of their registers. You will run out of registers very soon if you do that. So reuse registers, but make sure that the register that you are reusing is no longer, you can actually overwrite it. So the result that it currently holds is not going to be used in any code below. Okay, but usually most code would be would be perfectly fine using 10 or 18 registers that you are actually expected to use. It would be sufficient for most of the cases. Of course, if you need to store an array or something like that, you don't store it in your registers, right? You use your either dynamically allocated memory or data segment or stack, and stack would probably not be typical, but you can still do that. How big is the stack? Like how much could we theoretically store in? That depends on the number of of how big your program is and how actively it is using stack, right? Stack is something that you are using and you totally control, what is in your stack. So we will talk about it in just a few slides. There will be a diagram showing the memory structure of a MIPS processor. So here are other instructions that facilitate procedure calls. We already, excuse me, we already discussed them. So JAL is jump to an address and link, or jump and link. So this is what you use to call the procedure, and when the callee returns, it calls JR and specifies the RA as the address that contains the address to which we should return. All right, and here's their code that we just went over. So that is exactly the C code that was in their example that we reviewed. And yeah, so that's their leaf, and that's it. Okay, so we reviewed that already. Non-leaf are procedures that have nested calls that call other procedures. And as we discussed, it is important to save the RA, the return address. And it is also important to save any temps or any arguments, any A registers that you need after the call to the callee, right? Because the callee, of course, to call the callee, you may need to pass arguments in A registers, and the callee may override T registers without letting you know. So it's important that you take care of that in their caller before making a call to their sub procedure. Homework 3 is going to be tough. It's not easy. I have to agree. So please start early. Okay, it's still a week, right? So it's due almost. It's due on Thursday next week. So today is Friday, so it's a week. But please, most of the students would not be able to get it done in an hour. Okay, so do not plan it unless you have had prior experience with MIPS, or which is generally, very very good with that kind of stuff. Okay, if I had to guess, I would say more like 6 hours with all the debugging, if you're lucky. Okay. Well, we are learning some of the material for the homework today. So remember, I told you to start earlier because like their whole loop thing you could have written before. So the stuff that we learned today is dynamic memory, which you could you could have done without it. So clearly, the algorithm, the multiplication algorithm for the matrices does not depend on where your matrices are, whether they are statically located or dynamically located. And then the other thing that we learned today is procedures. But again, the code that you could have started working on could be just one procedure, and you could have just already verified, written and debugged and verified the whole matrix multiplication thing. Okay, so just to make it clear, and yeah, and you already have your C code from homework 1, so you can use that to help you with the transition. How fast could you do it? I don't know. I don't think a lot less than 4 hours. That would be my guess. But I don't know. So don't quote me on this. So it will take some time. Definitely start early, please. Hopefully you already started. Then it would be easier. Okay. Yeah. There's a hack. Take your code, compile it, save the assembly code, and is a submission. Yeah, but we will probably notice. So please don't try to play the system. And speaking of this, right, we were told that some people might have used illegally electronic devices on the last exam. Okay, so our proctors did not notice that, and that's why we are not exactly sure 100%, but it was brought to our attention, and I asked our rotation mentors to watch closer to make sure that all students comply with the policy. Okay, so please, no electronic devices, not even a calculator. There was nothing on that test, last test, that would require the use of a calculator. I'm assuming all students in this class, right? You are second year students. You should be able to take 20% of 250 by hand, or add 60 and 85 by hand. Right? I don't think it's asking too much. So you don't need the calculator for that kind of stuff. Okay. So yeah, we will keep a closer eye on that, and yeah, please just don't do it, because there's the penalty. So if you do use any electronic devices, we're not gonna even look into what you used it for. Did you use it to add two and two, or did you use it to Google the solution? Right? We won't be able to request that you know give up your that you hand over your device. It's your device. We cannot we cannot touch it. But if we notice that you use it, any device, phone, calculator, smartwatch, anything like that, it's immediate zero on the exam, 5-point deduction of the overall course grade, and their academic integrity violation form, because it is classified as academic integrity violation under the clause that says prohibited materials. All electronic devices are clearly prohibited on the exam. On the title page, if you read it, every exam says what is prohibited. Hey Siri, what is the answer to question 6? Yeah, it's funny. Okay. Can we use a non-electronic calculator? A mechanical calculator would be nice. Would be allowed. Okay. If you get one. Abacus. Yeah. Abacus I think is fine. Okay. Because with Abacus, we know that you only do what it allows you to do. With some gadget, we don't know whether it's calculator or it can actually or it actually has internet access, right? Okay, yeah, pencil is a solid calculator, or your mind is even a better calculator. We are allowing you to use your brains. Okay, so that is allowed without any limitations. All right, so moving forward. So that's the non-leaf procedure example. This is the factorial code, and you have it in your example, so you don't have to type it from the slides. I've already done this for you. So if you look at this factorial s, that's exactly this example. Well, maybe not exactly, but it is the computation of the factorial. So if we look at this code, we see that, well, here's our main. We do the regular thing. We are storing array because main is going to be calling factorial. So then we read in an integer value. So that was straightforward. And then we call the fact, the factorial. And then that factorial does its thing. And when it returns, we have v0, the return value from the factorial, and we just print it. Okay, that's it. And then we restore the stack and a return. So this return thing will be different slightly depending on the simulator that you're using. So this code works fine for QtSpim. For Mars, you would do syscall, so-called exit syscall. So you restore the stack as that doesn't change. But instead of calling JR array, you just set up syscall 10 and you call that syscall. And you could see that in some of my examples, right? For example, here that's example, right? You make a syscall 10 and that works with Mars. So on exam, either way, it's fine. We don't care. Okay, either way. But if you're using a particular simulator for to debug your code, this is something that you might be otherwise surprised why it's not working. It's because they are different simulators. They have slightly different expectations of how main should return to their calling environment. All right. So now the factorial function itself, the procedure. So it's is it a leaf or non-leaf? Well, we see that it is calling itself, right? Because it's recursive. So this is a recursive implementation of fact. So it's a non-leaf and leaf kind of at the same time, but the general case it's not leaf, non-leaf because it calls another function. So that's why we have to save RA, we have to save A0 because it's an argument and it will be overwritten as you're preparing to make a recursive call. So this is our base case, right? So we are testing, for the base case. If we have a base case, we just return to the caller, we are done. If not, then we make a recursive call. Okay, and that's it. And so this part is just a mirror reflection of our prep work where we were saving stuff to stack. Note how we pushed two values at once. Well, not at once, but we adjust the stack pointer by -8 so that we can store two values without making an additional modification to SP. We stored RA and we stored A0. And here we just restoring their what we saved, and of course we have to multiply the result of their recursive call with the result of this call to get their value that we are going to return to their caller. Okay, so that's that example. And finally, local data on the stack and the overall memory structure. So this is how we usually picture memory. Lower addresses are at the bottom, higher addresses are up top. And our stack is, for a procedure, is their memory that starts at FP. FP is the frame pointer. And like I said, originally, when you just call their procedure, FP and SP are the same. And then as you use SP, you decrement it so it goes down, as shown in this part B. So it ever gets to the part in the end. I'm not sure which part at the end. So if you're using too much stack, it will eventually run over the data segment. All right, so it's gonna be and it's not gonna be good, right? So you don't want that. So FP stays at a relative 0 point. Yeah, it's a relative 0 point for that particular procedure. For different procedures, it's gonna be different, right? Because if you have a nested procedure, then for the next procedure, FP will be here where the stack pointer for the previous call, for the call that is higher in the call chain, ended. So when that stack frame ended, that's where next one begins. Okay. And so this is the layout of the overall memory in MIPS. So you see that we have our code segment, text/code, that starts at this address 0040 and then 4 zeros. This is the initial value of the program counter PC. So whenever the processor is reset, just by hardware, electronically, PC is initialized to this address, always in the MIPS architecture. And so your program is stored here, and it is supposed to not take more than the size of this segment, of this text code segment, because at this address, 1004 zeros, our static data segment starts. And this static data contains the data that is statically allocated. So when you write in your code, when you write .data, and we have seen examples of using that .data a lot, right? So this is actually stored in this data segment or static data segment. And so this segment goes all the way up to 1001 4 zeros. And so it's 64 64 kilobytes in size. And then at address 1001 and 4 zeros, dynamic data starts. Okay, so this GP pointer is halfway through the static data. Why is it halfway? Because that allows you to use signed offset to refer to any part of this static data segment. Because we will see when we discuss memory when we discussed the internal structure of different. I think we already actually discussed it. Okay, so let me actually find it. No. All right. So then it's coming up soon. We will discuss the. Oh, no, it's here. Yeah. So we already discussed it. I was right. So this is the I format instruction, and note how this offset or address is 16 bits, but it's signed, as you can see. So the amount of offset can be from negative 32K, 32 kilobytes, to positive 32K. Well, of course, it's not symmetrical by one, but it's roughly negative 32K to positive 32K. And that's why we have to put their GP in the middle of their of our static data segment, so that using this signed offset, we can address any location within this static data segment, which has the size of 64K. Okay. And so then next is dynamic data and stack. They grow towards each other. Dynamic data is what you get when you make sbreak syscall with syscall 9, and stack is you control your stack yourself. There's no compiler between you and the hardware. You are the compiler, right? So you are writing instructions, and that's it. There's no other generated code. So you decide how to use stack. And you see it starts from the highest possible address, and then it grows down. Okay. So that's stack. All right. And so, excuse me. Then character data. So far we've been dealing with data that was either words like integers, or that were ASCII Z strings. And ASCII Z strings were like arrays of characters, and we learned about their syscall to print strings, but we didn't really talk about how this whole thing works, since each character is only 1 byte. So MIPS uses ASCII for characters, so it does not know Unicode. So Unicode is a more advanced encoding for characters that allows to represent more characters, because it uses 32 bits and actually more. It can represent 64-bit and 128-bit characters. So that's a little more advanced stuff. MIPS is treating each character as 1 byte as an ASCII, and we have seen their ASCII character table. And actually, if you look in your reference card, right? So there's a bunch of useful stuff here. So one thing is actually the convention, the call convention, and which registers are used for which purpose. And then here we have basic instruction formats. So we just looked at I once again, I format, and their slides around that slide with an I format instruction, R and J instructions. So R are instructions that have 3 registers and no immediate value and no address. So those are things like add, and I is corresponds to instructions with an immediate value. So it's like add I, X or I, or any other I with an immediate. And J are for instructions that have an address. Okay, and that can be a BQ because it has an address. It can be J, it can be JAL, and in MIPS, yes, instructions are only 32 bits long. Okay, and more importantly, in this reference set, it says for not for all instructions, but for all their basic core instructions, which format they follow. So if you're wondering, like, oh, branch on equal, which instruction is it? Oh, it's actually I instruction. It's not. Like I just said. Yeah, I misspoke. It's not a J instruction. Sorry, it's an I instruction, right? So J instructions are jump and jump and link. Okay. So those two. So branch is an I instruction. Isn't add IU 40 bits? No, it's not, because all instructions have to be 32 bits. And that's why the immediate value, as you can see, is only 16 bits. See the numbers 0, 0 to 15. And that means you cannot do add immediate with something that is, let's say more than, takes more than 16 bits to represent. So if we look at add I, you see how it says sign ext_im, right? So that says immediate value sign extended, which means it is signed. So that means that if you have this immediate value here, it is treated as a 2's complement notation. So you can have at most from negative 32K to positive 32K for the immediate value here. So if you want to add an immediate value that is greater than that, all right, you have to use, you have to store that value in the memory. Let's say in your data segment, and then load it from memory into R, and then use just regular R instruction. Okay, is that making sense? So if you want to add 64K to the value of the register, add I is not going to help you. Okay, because you will not be able, it will not be able to encode your immediate value using just these 16 bits. Okay, with one instruction. So of course, it would be possible with multiple instructions. Okay, and actually, to that matter, let me open some example for you, like 11. All right, and let me comment out this for now, and let's just try, because I think you you covered a very important, you touched upon a very important question. Okay, so add T0 and T0 and something like that. Okay, so let's look at the code, and we see how this instruction is encoded. And you see that the machine code for that instruction it just exactly follows this format. So if you use this table, and opcode you can find from this table. So here, and ASCII symbols are here as well. All right. So for add I, you need to take their opcode, and then for RS and RT, you just use the encoding for the register, and they are taken from this table. So this is their code. The number is the code for the register number. Note how it is 5 bytes exactly, because we have 32 registers. Each is numbered. So if we want to encode register 0, we just put 5 zeros in binary in our, let's say, RT. Okay. And so if we translate the instruction from our mnemonic form with, more or less human understandable way, method to their code, to just, 32 bits, 32 ones and zeros, for this instruction, for this add I, we will get exactly this code, 2108838800 in hexadecimal. And note how their immediate value is coded here in this in this third argument. So what happens if we change it to this, for example? Okay, we see that we are not getting the right value, right? So this value is not negative 100,000, right? It's actually -2. Okay, so we see that instead of, and the compiler in this case is helping us because it is actually replacing this single instruction that we used to have with 1, 2, 3 instructions. And you see how now there's this space here when there's no instruction from our source code, because this one instruction 13 is generating 3 instructions to make sure that we deal with this fact that we no longer can fit our immediate value in 16 bits. And the way this code works is LUI is load upper immediate. So let's actually run this code step by step. And yeah, this is just saving stack, right? So first we load this value into register 1, so you can track it here, right? So that would be register 1. This is the AT, the assembly temporary register. That is, we never use it explicitly. It's reserved for cases like when the compiler generates additional instructions. But you see that it is referenced, and you see that it will be loaded with FFFE. So that's why it's called LUI, load upper. We loaded the upper half of this register with the immediate value. Okay. And we took, of course, the last 4 hexadecimal digits from our from our immediate value, and we loaded into the upper half of register 1, register AT, and then see what happens. We ORed with 7960, and then we performed our addition. Okay, and T0 is now this value. So this value that we ended up having in register AT is actually negative 100,000. So see how we represent. So we had to take this extra step to move, to kind of form this negative 100,000 in the register AT, and then we added register AT to register T0 and got our result. Okay, and before, like I mentioned before, if we had 32,000, that was not necessary. See, it's just one instruction because everything fits. This immediate value fits in 16 bits. Okay, making sense? And so this example that I actually didn't want to show you, right? So when we are talking about bytes, we need to be cognizant of the so-called word alignment. So if you're using LW instruction, then it will expect that their address is a multiple of 4. Otherwise, it's not going to work. So let's look at this example. We have this, and yeah, so hopefully this is reminiscent of your question 6 on the exam. And yeah, so we will review the solution, and it is it is not that big, but I understand why it was challenging for many of you. So I completely feel it. Believe me. So note that we have ASCII characters. So the question is, how many characters would I need? Would actually hex prefix represent? Well, hex prefix is the address of the first byte of this. So it would be the address of this byte that contains character 0. And then there are 2 more characters, X and null terminator, because it's an ASCII Z, right? It has a null terminator. So how many bytes would take to represent this? 2 bytes, 1 for the digit, for the character itself, and 1 for the null terminator. So in your exam, you wanted to go over this array, and you had to increment their offset by 2, because each of those digits is 2 bytes apart from each other. Yeah, they're characters, and it says ASCII Z, and we gave you that line, right? So it would be a lot harder if we didn't tell you anything, but we gave you those parts, and those are ASCII characters. Okay, so what if I now have this code? I'm loading address of hex digits into T0, and I'm trying to load word into T1 from hex digits. And if we try to compile it, okay, you see that did I not? Okay, yeah. So let's yeah, this one works. So let's see at the code. So and let's look at our at our labels. So this is an important list of labels and the addresses that they represent. Okay, main is the entrance point into our program. It's 0040 for zeros, and then hex prefix is that, and then hex digits is this. It ends in 3. Why? Well, because we immediately before hex digits we had 0, 1, 2. Okay, so 3 characters, and data segment starts at this address 1001 and all zeros. That's the start of their data segment, right? And it is shown like right here. You can see. Okay, so then when we load address of hex digits, it does this, right? So it loaded. We can load any address into any register. There's nothing wrong with it. And now we are trying to load from hex digits, which we know is this 1001 and 303 into T1. So we have to go to that memory address and load the word 4 bytes. And when we try to do that, you see that here it generates an error because it says that fetch address is not aligned on word boundary. In other words, if we are reading a word, we only can read from addresses that are integer divisible by 4. Okay, so we can not read a word, like one part of the word from one word, another part of the word from another word. We cannot read across word boundaries. That's why this address is not a valid address to read a word from. Right? If we need to read bytes, it's fine. But if we are reading words or half words, it's not fine. For half words, we have to only read from even addresses, not odd. Okay. For words, we have to read from addresses that are integer divisible by 4. That's why we can, change this to something a little different. Let's say I want to use my GP pointer, and remember, GP points to halfway through their data segment. So if we use this offset 8004, we should read from the address 4. So that would be this 0 after character 0. Well, to make our life easier, we actually want to align our data in this particular case so that hex digits starts at the word boundary. And so we use this align to. 2 is actually their exponent, so it will align to 2 power of 2 to the second power, to 4. Okay, and if we now run this code, we see what has changed. See how this is now 1001 and 0004. Okay, and now if we run this code, let me clear the messages. If we run the same code, and you see that it runs without any issues, right? Because when we are loading here into T0, we are loading from the address which ends in 4. Do I think Mars is better than QSPIM for developing with MIPS? I think they are different, but they are both powerful enough. I don't think there's a significant difference. I'd say it's more of a personal preference more than anything else. And I use both of them interchangeably. So I think it's even better if you could use them both. Okay, so then the GP example. All right, so that was alignment. That's why this example is called GP alignment test. Okay, so I actually didn't comment out the line I was talking about. So let me comment it out actually, and you see that the code runs without any errors, right? So we went through this code and it ran successfully. It loaded their value, and you see 30 and 31. So this is 0, null, 1, null. So those are characters from our data segment. So those are these first 2 characters. 0 has the code of 30. We have it here. And 1 has a code of ASCII code of 31. We can see it here. And you see those null terminators are here. Right? So it all worked successfully. And now if we want to do if we want to do with GP is halfway through the segment. So if we want to read the same thing at address 1001,004, we have to use this offset 8004 because GP is itself at 1000, 8000. And if we now run this code, let's see what happens. So we load hex digits here. it's 1004 right here in T0. And now we do the same with GP, and you see T1 has the same, it has the same value as T2 and T1 have the same value. We read the same thing because first thing we were reading from T0 and it had this address, and the second one we had this AT register that has the same value that we obtained by using GP with this offset. Okay, so that's that. And note how LW is an immediate instruction. That's why any offset greater than what can be represented using 16 bits would require additional instructions. Note how here we have 3 instructions. Okay, and it's it's kind of very similar to what we observed before. Something that I showed you earlier with add and add I, right? So if we by any chance could read the value from that is below 1001 four zeros, like at offset 7FFF from GP. Let's see, and look how we only use one instruction, okay, to do that. Right. So that again kind of brings us back to this memory thing, right? So this boundary here, let me write it. There's no register that points to it exclusively, but this boundary here is 1001 1000, and it's hex, of course, right? So I will write this little hex here. So that's this address. So GP is exactly in the middle of this static data. And we see how all values that are in this segment, they are within 32K from GP, and therefore they can be accessed with one instruction. Anything that is greater, so here, will require 3 instructions because the offset no longer fits into 16 bits, and that's why the compiler has to generate additional instructions to deal with that, which we just have seen. All right, so that means that we should strive to use this static data region because it actually works faster, right? But of course, so you can change in most simulators. You can change, you can tweak where your segments start and end to make sure your programs are efficient. All right. So to deal with bytes, if we want to deal with bytes by themselves, we obviously need different instructions, right? Because if we use load word, it will load the whole word. And if we only need to load the ASCII code for one character, we would need to use LB, as this example shows. And in this case, offset plus their base register. It doesn't have to be divisible by 4 or 2. It can be, it's a byte address, so it can be any valid address. And this offset is sign extended, as we have seen, so it is a signed offset. So if we want to treat it as unsigned, we need to use LBU, load byte unsigned, and similarly for store byte, so SB is to store byte. Okay, and we can also use LH, load high, and load high unsigned. So that is to load the value into the high part of the register, because LB would sign extend their value and load it into the lower part, least significant part of the register. If we want to load it into the most significant part of the register, we would have to use LH, and then LHU works the same way, and of course SB and SH are kind of complement of each other, right? SH stores the value from the high part of RT into the byte that is in memory given by RS plus offset. Okay, and here is a string copy example. So pretty straightforward. We also have it in, I also have it already typed in my examples, so please run it and review how it works. So this is the C code. We just copy string from one character array to another, character by character, until we hit their null terminator, and we need to translate this into MIPS, and the code is pretty straightforward. So here we just deal with, we're just doing our, saving their S register because we are going to change it. So that is our responsibility for our caller, and then here S0 will be our I. So it's helpful to kind of have even for yourself, like you can have like a table. I is S0, and then we need to get the address of y sub I in T1. So we load it from the arguments. So we assume that str copy takes A1, takes address of y string in A1, and it takes their address of their other string. It should be A0, and I'm trying to find it. Yeah, it's here. Okay, so that's their those are arguments. So they correspond to this and this, right? So addresses of x and y are in A0, A1. And so you can actually write it down here again as you're debugging your code. It is, so it would be A1 would be y, and A2 would be x. So this is my y. Sorry. Okay, and so now this is their main thing that performs copying. So we first load byte from y byte at offset I, which is S0. But we cannot, so this thing here, it has to be a constant, right? So we cannot have a register as both the base address and the offset. So if we need something like that, we have to add the offset and the base address ourselves, which we do here when we add the base address A1 and the offset as 0. We put it into T1, and then we use T1 as the address from which to load the byte. And then we use just 0 as the offset. And so we load the byte that we are there, which corresponds to the character that we are copying into T2, and then we store from T2 into T3, where T3 is the address of the destination, right? It's the base address of X, A0, and the same displacement, the same offset as 0. We put it into T3 and use it as an address. Okay. So why does it need 2 times 4 to I when doing address copying? So you are referring to this. It's because we are storing the value of S0. S0 is a register. It's 32 bits, so it's 4 bytes. Memory is byte addressable, so when we push 4 bytes into stack, we have to adjust stack pointer by 4. All right, so this is just their condition for 0. So if T2 is 0, it means we reach the null terminated character, and then we quit, we go to L2 from here. Okay, otherwise we increment our I, and we continue our loop. Okay, and when we are done, all we have to do is restore S0 from stack and return to the caller. It's this last instruction. Okay, so note that the return value is void, so we don't have to worry about returning anything. So we don't put anything in V0. Now, why don't you SLL T1 by 2? SLL T1 by 2. We don't. So T1 is the sum of. All right. So let's say A1 is something like 1001000, right? Then we want to go through each byte. So we want to go through byte. It's the same value that ends in 1, 2, and 3, because we are dealing with characters, right? We are not dealing with words. So each byte, each character is 1 byte, and that's why we have to go through bytes, not through words, right? If we increment by 4, which would be your proposed SLL T1 by 2, we would jump from 0 0 to 4, right? So we would only copy every fourth character, not every single character. Okay, making sense? All right, so this is something that we already discussed and reviewed. 32 bits constant with the immediate format, we cannot do it, right? We only have 16 bits in the field of the I instruction, and that's why if we have to, load an immediate value, a constant that is greater, that cannot be represented using 16 bits, we have to use some additional instructions, and the compiler would typically, as we have seen, generate those instructions for us, but we have to understand what those instructions are. Okay, so LUI is load upper immediate, so it loads the upper part of the register, this register, with the constant. Okay, so and with the 16 bits of the constant, because this LUI itself is an immediate instruction. So this constant can only be 32 bits. Can only be 16 bits, right? So it copies the 16-bit constant to the left part, to the left half word of the register RT. So when we do LUI or LHI, it's the same thing, 61 into S0, it takes 61 and puts it here, as this example shows, and then we OR it with something else. Remember why it is important to know like how all the masks work with OR and 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 XOR, and so we OR it with this value. This value 2000. This is decimal, right? So it's 2304. It's this part. So we kind of see how we glued the value that we wanted from two pieces. First, we grabbed the one piece, put it in the upper half of the register, and then we masked with a value so that we effectively combined it into the value that we wanted, from two parts. All right, and with an int array, each int takes 4 bytes to store, so the starting memory address of each int within an array is a multiple of 4. Yes, that is correct. All right, so branch addressing, that's all right, so for branch instructions, we see the format. Okay, so it's an immediate instruction, as we have seen, and that's why we can only go as far as this offset allows us. It's a so-called PC relative addressing. So the way it works, for a branch command, and it's a command like BEQ or BNE. If their condition is true, depending on whether it's BEQ or BNE, we compare, in both cases, we compare RS and RT, and then if the condition is satisfied, we jump to their address. And this address, there is only their displacement, is only the offset, right? It's only 16 bits, and it's relative to the current PC, to the current program counter. Since this address is the address of the word, all our instructions are word aligned. We do not need to store the two least significant bits of the offset because they're always going to be 0. And that's why we simply decide to not store them. And when we use this offset from the instruction to calculate their actual effective address, we take this offset and multiply by 4. And since it's relative to PC, we add it to the current PC. Of course, this offset can be both negative and positive, right? And note that PC is already incremented by 4 at this time, so we have to, adjust for that. All right. So that's how branch instruction worked. Okay. So note that there is this limit as to how far you can branch from the given point. If you want to go very, very far in your code, it's not going to work with one instruction at least. So you would have to do some tricks. So jump addressing is a very simple instruction format. It's J. You see that because there are no registers to encode, their entire machine code is just 6 bits, six bits of opcode and their address. The address, however, cannot be full 32 bits, obviously, right? Because we have to store uh, opcode as well, operation code, OP. So address takes 26 bits. So as before, we don't need to store their 2 least significant bits. That's why we just shift address 2 positions left when we use it. Address that we obtained from their instruction code, and we just use their 4 most significant bits from their program counter. So as you can see, the range of jumps, unconditional jumps, J and JL, is a lot higher than the conditional jumps, right? Than here. Okay, and note that in conditional branches, the target address is added to PC. In jump address, we just take their 4 most significant bits from the PC. So we are not really adding to the current PC, at least not directly. We are taking into account the current PC, but you can see you see that we are not. It's not exactly relative because we are not just simply adding to the current PC. All right, and here's the second pop quiz for today for you. And I guess I just need to open it. All right, should be open now. All right, and we have a few minutes left. Okay, so yeah, we can cover this. All right, so target address example is the loop that we have seen before in an example before, and you can see how this relative jumping works. So when we had this B and E here, we have exit label, but in fact, their value in their machine instruction itself in the machine code is 2 because we are jumping 2 instructions ahead, 1 and 2, right? So their PC at this point would be 800 and then 16, and then 2 is multiplied by 4. So it is 8, so 16 and 8, 24. That's why the effective address would be 824. When we do J loop, the same thing happens, but it's not relative to the PC. So it's basically their highest bits from their PC and their displacement, the offset. And that's why it's not negative, right? We are going up, but this offset is not relative, and therefore it's not negative. All right, so what do we do if we need to branch far away? We cannot do this with a single conditional branch instruction. So we just, chain them together. So we branch to something that is within reach, as in this example, and then we branch again to, the destination that is further, right? So if you don't have enough gas to go 800 miles, you just, go 400 miles, get more gas, and go another 400 miles. That's the idea. So these are the addressing modes that we reviewed. It's a summary. We've talked about all of that already in MIPS. So this is immediate addressing. The immediate value is given in the instruction itself. This is register addressing, which means the address of the operand is given as the number of the register, like add instructions. This is base addressing. This is like your load word, store word instructions, where instruction contains their address, which is added with their contents of the register as the offset. This is PC relative addressing, where the address in the immediate field of the instruction is added with the value of the PC. That's why it's called relative, PC relative. And finally, pseudo direct addressing, right, where the address is pretty much the direct address we go to, but we still have to take 4 most significant bits from the PC because our address is not really large. The field is not large enough to represent a full 32-bit address. Okay, so that's all the addressing modes that we have in MIPS, and here is the third pop quiz for you for today. Yeah, let's stop here. Again, we didn't go over all the material that I was planning for, but hopefully we went over some examples, and hopefully that was useful. Please put your suggestions. Please, submittee forum is kind of dead. I was expecting it to be more active. Remember, people can earn extra credit points for actively answering questions on the forum, but for that to work, some other people have to be asking questions. Okay, please. I was actually expecting to see a lot of discussions on practice problem solutions, and we had some, but very few. So thank you for those people who did, bring those topics up. But I want to see more discussions. Okay, you were all scared from the exam. Well, that was before the exam. Yeah, a lot of people use Discord. I have my mentors, watching Discord. I don't think they reported any significant activity, at least in the academic Discord. Maybe people are using some other private channels that are not visible to us. But if so, if we don't see anything, we can't really we can't really help. All right, so please be active, and we will try to think what would be fair to do with this past test. Don't feel stressed out. Enjoy the weather. It's a beautiful day, and it's Friday again. We have a long weekend ahead of us. Hopefully, you can get some rest. Please get good night's sleep. Don't stay awake. You know, late, and enjoy your day. Enjoy your long weekend. Thank you for attending this lecture, and I'm looking forward to seeing you on Tuesday. Thank you, folks. Have a good one.